all will be well. All right. So, are there any comments, questions, concerns, or anything before we get started today? Don't forget, there is no class on Monday because of the job fair. Wednesday, the assignment for Chapter 4 is due, and then most likely on Friday, the next Friday, we'll have the first exam over Chapters 1 through 5.
Will that be in class? Or
No, it'll be take home, like everything else.
Okay.
No, because I mean, there's just the 6 of you or 5 of you that show up regularly, so. And I'm not gonna do that thing where we all like log into Zoom and I stare at people while they take the test.
When will the time frame be for the test?
A couple days. So I'll probably give it on Friday and make it due like that Wednesday, right after.
This is like off-topic kind of question, but is like everyone in here pretty much electrical/computer engineering?
Computer science.
Computer science. Okay. Just wondering.
Are you electrical?
Yeah, I'm like.
My man.
This is an electrical.
It is an electrical engineering class. And all these computer science folks are computer engineers, they just don't know it yet.
They don't know.
Yeah.
Hardware stresses me out.
What's up?
Hardware stresses me out. I'm just here for the software.
Yeah, so computer engineering, man. Computer engineering's around to be.
You're the opposite.
Yeah, software is not for me. I'm not trying to be a computer typing all day. Even though I probably will be.
Yeah, it's 2020, man. Like, there is no engineering job that doesn't involve writing code anymore. Like, it doesn't exist.
Yeah,
Unless you want to be like a construction engineer, but even then, probably still involves a little bit of writing code.
Yeah, but even those construction engineers, they probably won't use that code that they learned, and if they do need to write code, they'll probably hire someone who does know how to do it.
Probably. But yeah, no, if you're a double E and you don't like to code, you're going to have to get over that.
You say what?
So if you're a double E and you don't like to code, you're going to have to get over that. Even like a power systems engineer needs to know how to like code SCADA systems.
I would like to do coding and hardware, like mess with the hardware and then like have to go back and code it.
Yep.
Do whatever.
Yep. Okay. All right, so let's get into it today. This is the last thing between me and the weekend. All right. So up till now, we've been doing Boolean Algebra, right? All right, that was what Unit 3 is all about. That Unit 4 assignment that you guys will hopefully be working on was all about Boolean Algebra. Now, here's the deal, right? There are 2 main problems with Boolean Algebra. Algebra. Problem number 1. Someone on Discord asks, is assignment 4 due Wednesday? Yes, it's due on Wednesday. All right. Problem number 1 with Boolean Algebra is that it's hard. Like seriously, Boolean Algebra is tough. There's no way around that. It sucks to do it. It's not any fun. Well, it is. I think it's kind of fun, but I've just been doing it for a long time, and I, don't have a grade that's dependent upon my ability to do it. So I enjoy it, but it's hard. But what I mean by it's hard, not like in a sort of snowflakey, like, oh, it's so difficult kind of way, but there's no systematic approach. There is no which is what fundamentally makes it hard. No systematic approach to get an optimized solution. All right, you get a Boolean expression, and it's basically just soup, right? And we kind of started to develop a process where it's like, all right, try the uniting theorem first, and then the absorption theorem, and then the elimination theorem, right? But even that doesn't really work all the time. So there's no good systematic way to actually get your optimized solution, right? It's all sort of by trial and error and just messing around with it, which is, sort of stressful and difficult for most people. It's not very fun. Problem number 2 is that there is no way to tell when you've arrived at an optimal solution. Right? You go until you think it's optimized, or maybe you can't think of anything else to do with it using the Boolean algebra theorems, but you don't really know, like, is this the optimized solution? Have I taken a wrong turn somewhere? Right? Because remember, there's multiple sort of branching paths, and you may have done something 5 steps ago that leads you to a dead end, whereas if you've gone a different direction, you get a more optimal solution. And there's really no way to look at it and know one way or another what the deal is. So we need a way to be able to know definitively that we have an optimal solution. So those are the 2 problems with K-maps. We need a systematic approach, or that's the main problem with Boolean algebra. We need a systematic approach, and we need to know when we've arrived at an optimal solution. Enter the Karnaugh map. So today we're going to talk about 2 and 3 variable Karnaugh maps. All right. So we also call them just K-maps for short. Before we can directly talk about how a K-map works, we need to kind of bridge the gap between Boolean algebra and this technique that we're going to do, and we do that with the binary notation. I think we've talked about it before, but here let's just go ahead and recap it. Imagine that we have an expression. Let's do this. A, B prime, C, D prime, or A, B prime, C, D. Now what is that going to simplify to using the regular Boolean algebra? Not AC. Good. A, B prime, C. We can use the uniting theorem, right, for D prime and D to get A, B prime, and C. So that's what it optimizes to. Now the binary notation gives us a little bit of an easier way to look at it and identify when we can apply the uniting theorem. The Karnaugh map is basically just the uniting theorem over and over and over again. So what we do is, if a variable is non-inverted, then it gets to be a 1. If a variable is inverted, then it's a 0. And if a variable is missing, then it's a dash. So that looks like this. A, B prime, C, and D prime is going to be 1, 0, 1, 0. Or A, B prime, C, and D is 1, 0, 1, 1. And that equals A, B prime, C, 1, 0, 1, dash. So all we really do is notice where there's a variable that's not quite the same, right? So that's the same as that one. The B is 0 and 0. The C position is 1 and 1. But the D, we have D prime, and D, we have 0 and 1. So that's the one that's going to become a dash. That's the one that's going to be eliminated. And so when it's dashed out, it doesn't appear in the Boolean expression. Does that sort of make sense? Let's do a couple more examples of that. All right. Let's call this an example. And let's just say that we're given a function. F is a function of 4 variables, A, B, C, and D, and is equal to A, B prime, C, or A, B, C. Now it's important to note right off the bat that it's a function of 4 variables. There's A, B, C, and D. Even though our Boolean expression doesn't include D, we have to account for the fact that it was there at one point. So this is sort of a simplified, it's already been simplified a little bit. So A, B prime, and C is going to become 1, 0, 1, dash, or ABC is going to be 1, 1, 1, dash. Now that's going to equal what? If we look at our binary notation, the variable, or excuse me, the bit that's different is the one here in the B position. The A position is the same, the C position is the same. They both have dashes in the D position. So that means that our result here is going to be 1 dash 1 dash, which means that the Boolean algebra version of that is going to be A and C, since the B and the D are missing, or dashed, and the A and the C are both 1s. Does that make sense? So I think right off the bat, this is a much easier way to sort of look at the Boolean algebra expressions. It's a lot easier to just kind of look at the 1s and 0s and see like where is stuff missing or not quite fitting into an expression. Let's do another example. F is a function of A, B, C, and D, and is equal to A, B prime, C, D prime, or A, B prime, C prime, and D. Now, the binary notation A, B prime, C, and D prime is going to get us 1, 0, 1, 0, or A, B prime, C prime, and D is going to get us 1, 0, 0, 1. So now if we look, the A positions are the same, that's good. The B positions are the same, that's good. But the C position is different, and the D position is different. This means that these two terms have 2 bits that are different between them, which means that they don't combine. Right, so only if 1 bit is different between them.
So is that as simple as it gets?
Yeah.
Okay.
All right, one more. Let's say f is a function of A, B, C, and D, and is equal to A, B prime, C, or A, B, D. Let's do the binary notation. A, B prime, C is going to be 1, 0, 1, dash, or 1, 1, dash, 1. So, right off the bat, you may be inclined to think that these guys combine because you have 1, 0, 1 and 1, 1, 1. However, they don't combine because the dashes, if an expression in binary notation contains dashes, those dashes must be in the same location for it to combine. So despite the fact that we have 1, 0, 1 and 1, 1, 1, which appear to be 1 bit in difference with each other, the fact that the dashes are in different places, the first one is in the D position, the second one is in the C position, means that they don't combine. So we can sort of write down those rules. We'll say 2 terms represented in binary notation will combine if and only if 1, there is only 1 bit different, and to any dashes are in the same position. So, Two terms represented in binary notation will combine if and only if one, there's only one bit different, and two, any dashes are in the same position. So that's the binary notation. We're not going to spend a lot of time doing any work in the binary notation, but this kind of bridges the gap between Boolean algebra and K-maps. We're going to do this binary combination thing, but we're going to do it graphically. We're going to do it visually. So let's go ahead and take a look at K-maps. Let's start with two variable K-maps because they are super simple. So two variable K-map. All right. So K-map is a box. The box doesn't suck. Two. And we're going to cut the box in half vertically and horizontally. We're also going to add a little sort of stem coming out of the top left corner. That's our basic structure for a K-map. Copy it so that I can use it again. All right. So now if we have a truth table, so let's go ahead and jot one down. Let's have A and B and F on the output side. We have 0, 0, 0, 1, 1, 0, 1, 1. And let's say we have F is 1, 1, 0, 0. The first thing we do is we lay down our empty K-map. Why won't you? There we go. All right. So the way we're going to populate this K-map is thus. We're going to make a note of what function we're trying to solve for by labeling it at the top of the stem. And we're going to put the leftmost variable on the top side of the stem, the rightmost variable on the bottom side. We're going to label the top row, the A row, 0 and 1. And we're going to label the column, the B column, also 0 and 1. And what this does is everywhere we match things up, those are the min terms that we're going to get, right? So this top left column, or excuse me, top left box, excuse me, is 0, 0. The next one is 0, 1. The top right is 1, 0, and the bottom right is 1, 1. Does that make sense? We can also label them with decimal numbers by saying, 0, 1, 2, and 3. So now we're going to put all the stuff in the columns, we're going to put them into the boxes according to their min-term places. So we had 1s at 0 and 1, so we'll write 1 and 1, and we had 0s at 2 and 3. Just like that. That's the setup. So now we go to combine terms by just grouping them together. So we're going to go ahead and take a look at these terms that can group together. So 1 and 1 in 0 and 1, they have the bits 0, 0 and 0, 1, which means they have one bit in difference between them. So they can be combined. We're going to combine them by simply just drawing a box around them. There we go. So we're just going to group them up. And now we figure out what term that is by just looking at what the box, where the box fits. Notice that the box fits neatly inside the column for A equals 0, right? But it splits the difference between b equals 0 and b equals 1. Does everybody see that? That's how you identify it. So whatever the group, whatever sort of row or column the group fits in, that's the term. So this guy, this whole thing, is just a prime. So we'd say our whole function, f is a function of a and b is equal to a prime. And there we go. No Boolean algebra required to get our optimal solution. Now this is a simple example, but as we're going to see in a second, makes life a lot easier down the road. Cool. Any questions about that? All right. So let's just go ahead and move on to 3-variable K-maps. Because I got more interesting stuff to talk about. So 3-variable K-map. All right, let's go ahead and lay down a truth table for 3 variables. A, B, C gets us 0, 0, 0. I'll write them all out. Now let's say that f is 0, 0, 1, 1, 1, 0, 1, 0. Now our 3-variable map is going to be like two variable maps stacked on top of each other. It's going to look like this. 2. All right. And then we're going to cut it in half. Horizontally, we'll cut each top part and bottom part in half horizontally. And then we'll cut the whole thing in half vertically. There. And again, we'll add that little stem onto the side. There we go. And now we're going to populate it exactly the same way. Let me make a copy so I can not have to draw it again. All right. We're going to throw an F there at the top of the stem. Now, since there's 3 variables, we're still going to put A, the leftmost variable, on the top of the stem, and we'll combine BC on the bottom side. We'll label the top 2 columns, 0 and 1, for A prime and A. And then down here on the left side, it gets a little bit tricky. We're still going to go, we're going to do 2 variables. We're going to go 0, 0, 0, 1, 1, 1, and 1, 0. So notice that we didn't go 0, 1, 2, 3. We instead went 0, 1, 3, 2. And the reason for that is, again, because we want to combine things, we have to adhere to that rule that things, adjacent cells, have to be only different by 1 bit. So we use this sequence, which is called a gray code, so that all of the cells that are next to each other are only different by 1 bit. So 0, 1 to 1, 1 is just 1 bit change, and then 1, 1 to 1, 0 is also only 1 bit change. Let me go ahead and label the boxes themselves. Thank you, OneDrive. So that's 0, 0, 0, 0, 0, 1, 1, 1, 0, 1, 0. Now I have 1, 0, 0, 1, 0, 1, 1, 1, 1, and 1, 1, 0. And we'll go ahead and populate our 1s and 0s. So we have 0s at 0 and 1, 1s at 2, 3, and 4. So 2, 3, and 4. 0 at 5, a 1 at 6, and a 0 at 7. All right, so there's the setup. Now we're ready to go ahead and combine things. So like I said, we got to create groups to combine terms. We got to do it with stuff that's adjacent. Now there's a couple of rules. One rule is that you can only create rectangles, so you can't create like weird shapes. You can't create like L shapes or T shapes or anything like that. And the size of the boxes, the size of the groupings have to be powers of 2. So you can have one cell by itself, that's 1. You can combine 2, you can combine 4, you can combine 8, but you can't have a group of 3, you can't have a group of 5, or anything like that. It has to be a power of 2. Otherwise it just doesn't work out. Does that make sense? Or do we accept that at least? So here, if we want to do those things, let's take a look. The first thing I'm going to combine is 0, 1, 1 and 0, 1, 0. Let's see. And so we notice from that it fits inside the column for a equals 0. And here it's inside 1, 1 and 1, 0, which means that the b stays the same. B stays equal to 1. But a changes between 1 and 0. So this term is going to be a prime and b. Does that make sense? William asks, what if it goes diagonally? It can't go diagonally. Because diagonal terms aren't adjacent, right? So 0, 1, 0, I can change this in a second, man. 0, 1, 0 and 1, 1, 1 have 2 bits in difference, so you can't combine those terms. All right, what's that?
How do you know if it's going to be, if it was a prime or b? How do you tell it again?
You look and see where the differences are. So for this box, so we see that it's in the a equals 0 column, right? That's easy. A prime is going to be part of it. But we have BC, so it's b equals 0, b equals 0, b equals 0, but c equals 1, b equals 1, c equals 1, b equals 1, c equals 0. So here, remember, so this group is in these 2 bottom rows, right? And these bottom 2 rows have b equals 1, but they have c equals 1 and c equals 0.
Okay.
So which one changes?
C.
Yes, whichever one changes is out.
Okay, so if it was flipped like the other way around, for example, well, that would, you couldn't flip it.
What do you mean by flip it around?
Like if the 1, 1 was on the bottom, or
No, I mean it just doesn't set up that way.
no, yeah, that's right. Because
Yeah.
this was because of F.
Yeah, it's just not part of the process.
Okay.
Yes.
Why is it good at A prime?
What's that?
Why is it good at A prime?
Because this grouping is in the column for a equals 0. And remember our binary notation means it's a prime.
So if the 1, 1 was on the right hand side, what would it be?
Say that again?
If the 1, 1 was on the right hand side instead of the left, what would it be?
I'm sorry, I totally don't understand that.
So
The grouping of
the
1, 1.
grouping
Like
of
it was
one-
yours on
yeah.
that column,
Oh, why'd you call it the 1, 1? Oh, you
Oh,
mean
the
like
one,
the
yeah,
yeah.
the one, yeah.
Okay, if the group was over here, yeah. Well, let's take a look. Let me draw that out for the folks on the Discord. The question was, what if, let's say we had 1 there, and we grouped it like that. Now that would be, so the column is in the A, equals 1, so we know it's going to be A. And then it's in the same 2 rows, so it would be A, B.
Okay. And then C goes away once again because it's
Yeah.
it changes.
Yeah. What's that?
So if they were both 1, 1, would you group all of them together?
Yeah, so check this out. So we've got
Yeah.
these 2 guys, A prime and B prime and A. Well, we already know that. What if we have, we can use a little Boolean algebra too. If we had, so here we have AB or A prime B. Using Boolean algebra, what's that going to simplify to?
A, B.
It's going to simplify to B, right?
Oh, B. That's right.
Now, if we go ahead and treat it, if we ignore the Boolean algebra and just do it the K-map way, let me trying to erase these guys. There we go. Now if I combine them like that, then we see that the box now, first off, it's a box, it's a rectangle. That's good. It's a power, it's at 4, so it's power 2, so it's a valid move. But now look, it splits A equals 0 and 1, so A is out, right? It's still in this place where C goes from 1 to 0, so C is out, but it's in the place where B is equal to 1, so it stays at B, right?
Okay.
So that means it's equal to B. Yeah, because B is the only one that stays the same.
The Boolean Algebra example helped a lot.
Good, glad. Yeah. So the idea here is that we're going to use this technique. There's nothing that we're going to do here that you can't also do in Boolean Algebra. The advantage here is that it's sort of a visual way to do it. Where you kind of look at everything and draw these boxes, which the majority of people find a little bit more accessible and a lot easier to do than Boolean Algebra. But it's all the mechanics are all the same.
I feel like when the Boolean Algebra expressions get longer, it's more easy to mess up when you're doing it by hand. So
yeah, it's a lot easier to look at the table and say, well, this is,
sure.
we're just drawing boxes and stuff. Okay, just got a couple more examples before I let y'all go. Well, actually, let's just leave it right here. What's the deal with this top box? 1, 0, 0. That guy by itself. Can we combine it with anything?
No.
Yeah, we can.
We can. Is it?
So check it out. So 1, 0, 0 and 1, 1, 0. Are they different by only one bit? You bet. So the top rows and the bottom rows, you can actually think of the three-variable map as it curves around and touches each other. Right? So 0, 0, 0 and 0, 1, 0 is also only different by one bit. So the whole thing comes around. So the terms of the ends are themselves adjacent to each other.
So then you could combine all 6 terms?
Now you can't combine all. Well, first of all, there's only 5 terms,
All 5,
but you can't combine all 5 terms. Why not?
because that's not a power.
Because it's not a power of 2. So we can create this group of 4, and then we can take this. We can still use terms that we've already combined to make new groups. Now, what would that be equal to? It'd be A and C prime, yeah. Right? Because it's in the A equals 1 column. But here, since we're looking at the ends,
Oh, I didn't see.
yeah, see? It's got, so B changes, right? B goes from 0 to 1, but C stays the same, stays at 0 and 0, right? So it's A and C. All right, let's see here. All right, let's do a slightly different example. Let's kind of reverse, what I want to do is reverse engineer a K-map from an expression that's already simplified. So let's start with this. We'll say that F is a function of ABC. And is equal to, we're almost done, A, B, C prime, or B prime C, or A prime. So we're going to kind of reverse engineer this. Let me put in a new map. Paste. Get rid of that. All right. So let's put in the same stuff. We got F, we got A, we got BC, we got 0, 1, we got 0, 0, 0, 1, 1, 1, 1, 0. So now we kind of look at the terms themselves. So the first one I want to look at is A, B, C prime. Right? Now that's one whole minterm, right? Which means it's going to be just one place. So which cell is going to have a 1 in it because of that term?
Bottom right.
What's that?
The bottom right one.
The bottom right one. So A, B, C prime is going to be what? 1, 1, and 0, right? So yeah, so the bottom right one, the one that's 1, 1, and 0. Now, what about B prime C?
Would be 0, 1.
Yeah, it'd be 0, 1. It'd be this whole row too, right? Does that make sense? So B prime C, we're going to fill in the whole sort of group there. That would be B prime C. If you had those ones already and you made a group, it would be B prime C. Now what about A prime?
Would that be, it would be 0. Do the dashes, do we do anything with the dashes?
We don't do anything with dashes.
0, 0, 0.
Not just that.
And the bottom.
Not just that. Think about what grouping would give you just A prime without B's or C's.
The top right?
Not the top right,
Top left.
not the top left. The whole left side,
Oh.
right? Think about it. A prime is everywhere where A is equal to 0. So it would be all the way
Down.
down, just like that. Does that make sense?
Kind of.
Just because that whole A, like that whole.
Yeah, the term is
vertical-
A prime,
Oh.
which means that there's no B, there's no C, it doesn't matter. So it's
So that was
one
mean that all those were
everywhere.
equivalent to 1.
Yeah,
Okay, now that makes sense.
yeah. It's one's all the way down.
Because it's already given to us.
Exactly.
Okay, that makes sense.
So like I said, in this example, we're going backwards, right? We're starting with the expression, and we're kind of reverse engineering what the map would look like based on those expressions, including places where there's some overlap, right? The places where, you know, both B prime and C and A naught are both 1 at this cell.
Yeah. But we're allowed to overlap.
Or we're allowed to overlap, yeah. Because you would still group those terms together.
Yeah.
All right. One last thing. Suppose, oh, I gotta paste some stuff. Paste. I'm actually gonna paste in two maps. Copy and paste function in OneNote is terrible. Okay, that's good enough. So 2 maps now that I want to put the same function on. Let's say that f is a function of a, b, and c, and then is equal to, now I'm just going to list it out as a sum of minterms. 1, 3, oh, excuse me, not those. 0, 2, 5, 6, and 7. And we're actually going to put the same expression in both maps. So I'm going to put f on both ends, f and A, and B, C, and B, C, and 0, 1, and 0, 1, and 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and then we're going to fill in the things. So 1, 0, 2, 5, oh, I think I forgot one. 0, 1. Let me modify this just a little bit. 0, 1, 2, 5, 6, and 7. Otherwise the example doesn't work. So 0, 1, 2, 5, 6, and 7. And let's put zeros in the other places. And let's solve this. Now there's at least two different ways to solve this, right? So let's look at the left-hand side. Now the left-hand side, it's not a lot of good stuff, but I can group these terms and say this first one is, so A is equal to 0, B is equal to 0, C changes. So this is A, B, or I can group these two guys. And that would be, so A is equal to 1 and C is equal to 1, so A, C. And I can group these bottom two terms. And so that splits A, so that's just going to be B and C prime. Pretty straightforward, right? Any questions about that one?
Do not group the second row,
What do you mean?
0, 1. Do not group those ones together.
You can. So, well, not in this example. Here, once you have terms grouped, you don't need to do it again,
Okay.
right? Because that's just going to create. In fact, when you do that, we don't have time to show it right now, but if you were to do that and sort of lay it out with the Boolean algebra, that's actually what the consensus theorem means. You will get the consensus term between these two terms by combining them across cells that they've already included. So if you've already got a thing accounted for, don't do it again. You can double up only if you have to. Like if you need to use a term to get a better term for something else, but since everything's covered, there's no need to do it again.
Also, how come we go 0, 0, 0, 1, 1, 1, 1, 0, no?
That's because we talked about that already, man. That was
I forgot what you said.
Because they have to be adjacent, right? The rule is they have to be only 1 bit difference between each other.
Okay.
So if we want to be able to group these two, 0, 1, we have to go from 0, 1 to 1, 1.
Yeah.
And to 1, 0, right? Otherwise it doesn't work.
Okay.
That's the way it has to be set up. Liam asks, isn't the first one A prime B? Yep, you're absolutely right, Liam. That should be A prime B. All right, let's do the second map. Now the second map is the exact same map, but I'm going to solve it in a different way. I'm going to combine the top and bottom terms first to get, what, A prime, C prime. Then I'm going to group the 0 and 1, like we just talked about, because I can now, because now it's not covered up, to get B prime C. And I'm going to group these terms. And that's going to give me A and B. So, here's the deal. The same function we started with gave us the exact same map, but we solved it in 2 different ways. And in both ways, both times, we got solutions that were equivalently optimized by the metrics that we used to determine which one is better, how many terms, how many literals. They're exactly the same. They're both 3 literals and 3 terms and 6 literals, right? So is one of them better than the others? No. They are both equivalently optimized solutions. So it's possible to get it, just like in Boolean algebra, you can get functions that have equivalent solutions, but here it's a lot easier to see. And it's a lot easier to know that it's a lot faster to arrive at that. Because if you started with the Boolean algebra and done it, you wouldn't really know which one you got. But here you can actually look at it and say, all right, I just got 3 groups of 2, and I got 3 groups of 2. Those are exactly the same. There is no better way. I can't make any groups of 4. So I think it's a lot easier to look at it and say, yeah, I know I've got the optimized solution. Yeah?
So is this just kind of a way to check it to make sure you have the most optimized thing by drawing a second email?
You can't. I mean, I did it for this example. In practice, I would just sort of like scribble on the same one, right? And sort of mess it up.
Double check.
Yeah. So you kind of double check and think about, it's kind of like solving a Sudoku puzzle, right? You kind of look at it and say, all right, the goal is to create the fewest number of the largest boxes. So since we have the same number of the same size boxes, they're equivalent. And there is no way to create a smaller number of larger boxes. All right, perfect time. Let's see. One last thing is, while you're still kind of, since you're new to K-maps, and it takes a little practice, one thing that I always do, even now when I finish a K-map, just to make sure, even if I'm confident that I've done the optimal solution, you always just like take a beat and look at your Boolean expression and think to yourself, could I do anything with this with Boolean algebra? And hopefully the answer is no, but it's just a good like sort of check for yourself. Take a minute and be like, all right, A, B, A prime B, A prime C, B, C, is there anything I can do? No, I guess not. So
You couldn't group the AC and the BC prime together to make,
no,
no?
no.
Okay.
Hold on, to mess up another one. Aaron says, since B is 0 for both. Oh, yeah, that's totally right. Screwed that one all up, man. This one should also have been B prime. It's going fast, man. Alright, so that happens when you do it live. Okay, any other questions about that? That's all I got for you guys today. All right, cool. Well, in that case, like I said, don't forget, no class on Monday. So, enjoy the day off or go to the job fair. Hopefully you go to the job fair. Try to get a job. The Unit 4 assignment is going to be due Wednesday. The first exam that covers chapters 1 through 5 is going to be on Friday. Be sure to read through we'll finish chapter 5 on Wednesday. We won't do the chapter on 5 variable K-maps because they're insane. So a 4 variable map is like a big 4x4 grid. A 5 variable map is it's 3-dimensional. You have to draw like cubes on top of each other.
Oh.
I saw that and I was like, nah, I don't care. We're not doing that.
So, and then they connect it to.
Yeah, so they're 3-dimensional. It's 2 4 variable maps floating on top of each other, and you can draw the connections between them from top to bottom. Yeah, it is a super fun intellectual exercise.
That is a lot.
But I don't want to lecture on it, and I certainly don't want to test you guys on it, so we're just going to skip over that. If you want to come to my office hours and talk about 5 variable maps, we can do that, but we're not going to do it in class.
Artistic skills, right?
Yeah, right. It's hard to draw.
Or your 3-dimensional reasoning skills.
Yeah, right.
How do I